what we're going to be going over here is just a basic problem here in linear algebra, or what they might refer to as linear optimization or linear programming. And what we're going to be looking at here is where we're going to have two different products here, product X and product Y. And each of those products use some materials here, materials A, B, and C here. And the materials are only going to be available, a certain number of, or quantity of those materials are available here that are going to be used in these products. Now, what we're going to have to do here is we're going to optimize the amount of product X and product Y that we're going to manufacture here based on some profit function here. And so we can look at it in terms of dollars here, but the equation that we're going to be looking at is 3 times whatever number of product X we're making here plus 4 times whatever number of product Y we're making here is going to equal our profit. Okay, so when you're talking about these linear programming problems, you're going to have some function that you're trying to either maximize or minimize, and in this case we're trying to maximize it. Okay, so this is what we have to do here. We'll step through it number by number here. So the first thing you're going to start with is some table here. And again, we're going to have our inputs that we're going to be looking at here, or the use of our inputs are going to be for product X and product Y. And then we're going to have some maximum capacity or inputs for the 3 different materials that we're going to be looking at here. So we have the 3 different materials, material A, B, and C here. So for product X here, it's going to use material A. It's going to have 1 unit of material A and 1 unit of material B, 0 units here of material C. Product Y is going to use 1 unit of A, 0 units of B, and 1 unit of material C here. But the material that's available to us for manufacturing these products, we have a capacity or an input capacity here, a maximum number of units of materials that we can get for each. For material A, we can only get 7 units, material B would be 3 units, and material C here would be 6 units. So this is the basic problem we have to do, and we have to maximize, come up with a solution here, come up with the right product mix for X and Y here to maximize our profit. Okay, so that's the first thing we have to do. You have to set up a table as we described here. So the next thing we have to do, let's go down, we're going to have to set up some linear equations here because this is a linear optimization problem. So what we're going to start with, and we're going to step through this problem number by number here, assuming we don't have any understanding here of linear programming or linear optimization. So okay, we'll start with our constraints here. So the constraints are based on those 3 different inputs we have for our materials A, B, and C here. So you're going to have to set those up as your inputs here. And then the constraints are based on our table here. And what we're going to have here for material A, well, 1 unit here of X plus 1 unit here of Y here, equals, or has to be less than or equal to the capacity here for material A, or the input here, material A of 7 here. Okay, so that's what we're dealing with. And then for material B, these are constraints. These are our limitations here. For material B, what do we have here? Oh, product X uses 1 unit here and Y uses 0 here, but it has a maximum availability of 3 here. So the equation here would be X would have to be less than or equal to 3 here. First one was less than and equal to as well here. That's what that sign represents. And then for material C here, let's go up to our table. Product Y uses only 1 unit here, product X uses none. But it has a constraint here, or a maximum capacity of 6 here. So going down to our constraints here, Y, that 1 unit is shown here. Again, it has to be less than 6 here. And then, of course, in our case here, our X and Y values have to be greater than or equal to 0. We don't deal with negative amounts in this case here. Okay, so those are setting up our constraints here, our linear equation here based on our constraints. So the next thing we have to set up is some lines. We're going to be graphing this out on actually a 2 and a 3-dimensional plot here. But next thing you have to do is determine your graph here, the line. So what you want to do is you want to take these equations that you have here, these constraint equations here, and you want to solve them for Y or X. Really, you like to look at solving them all for Y here if you can. So for the first one here, and I'm just using the equal sign here, these are the way we're going to set up our plots or our lines here based on the equal sign here. So for Y, well, just move your X over on this side of the equation, so it's 7 or 7 minus x, that equals your y value. And then for x here, well, that has to be just it's equal to 3 here. There's no y value in on it. So that's equal to 3 here. And then, again, and that was for material B. First one was for material A. And then for material C, y equals 6. And again, x equals 0 and y equals 0 as well here. Okay, so that's for our graphing our lines here. We have to determine our line equations here. We've got based off our constraints. And our constraints come off our table here that we set up. Okay, so now let's go and let's look at how we'd plot that. Okay, so again, we're just looking at a 2D plot here. And what we're trying to look at is the line intersects here. So our y-axis is showing here from 0 up to 7 here, because that's, and then our x-axis is shown along here from 0 to 3 here. Okay, so let's work off our line off our graph here to set up those different lines. So let's first look at maybe x equals to 3. Okay, so when we're talking about x equals to 3, that x just stays constant at 3 and it moves up all the way. Y, as y increases from 0 to, in this case, 7 here, x just stays constant here at 3. And then let's look at our y equal to 6 here. Okay, and that was our red line here for the x equals to 3. And then our y equal to 6, well, y stays constant here at 6 as x increases here from 0 to whatever, 3 here. So we're going to have an intersecting point there. And then the only other function we have here, we have to graph, is this y equals 7 minus x here. So, okay, you just put in here at when x is equal to 0, that is here, y would be equal to 7 here, 0 and 7 here. Maybe I should have went through these other points here as well. So this this other point here that was 0 and 6 here, 0, x is 0, y is 6 here. And then we had our 0 and 0 point here. And then this other one here was x is equal to 3 here, y is equal to 0. Okay, so back to our line here, y equals 7 minus x. So when we had x equal to 0 here, that leaves our y equal to 7. So that gives us x 0, y 7 at this point. And then the other point, well, we can look at this point here. We're really looking at where we have these intersecting lines setting up a boundary here. So the next intersection would be here where it intersects with this green line where y equals 6. So we would set our y equals to 6 here, and that leaves what? 6 minus 7, minus x is going to leave 1 here for x. So we're going to have this intersection here, the blue line, with that constraint here, y equals 7 minus x, intersects with our green line here at y equals 6 here, at x equals to 1, y equals to 6. Okay, so that's where it intersects. So we're looking for all our intersecting points here within a bounds here. And then we come down to this line here where what? X equals 3, and what was y going to? If we put x equals to 3 here on that blue line, 3 minus 7 and minus 3 is going to equal y is equals 4. So that's our point here. 3x, 4y. Okay, so really what we're trying to do with this linear algebra here, this linear program, we're trying to come up with the bounds here. We're looking, we want to come up where we're going to be looking at really graphing a region here. We want to see where those different lines intersect here. Of course, we had an intersection up here, and then here it intersected with the x-axis equal to 0. But all we're really concerning with is the different intersections we have here that include all those lines. Because what we're going to look at here, we're going to be looking at, let's go over here and look at. So this is our feasible region here for the profit here. This green, what I'm showing here, that's the feasible region. That's really those different points that we looked at here. So you can see how they translate over here. So these constraints, these lines that we have here were the constraints, and these constraints create a region on a plane here. So this is the feasible region for our profit here. And then just remember our x and y's here, they have to be, they couldn't be less than 0 here for x and y quantities. And then for our x quantity here had to be equal to or less than 3 here. And then on the line here, all these are less than or equal to areas that we looked at here. Okay, so you understand our feasible region here. It was based off the graph that we did off our intersecting lines. Okay, so next thing we would do here, let's go and let's actually determine our different our maximum profit, because that's what we're trying to do here. So what you want to do is you want to check all the corner points. You really want to check all those different corner points that we're looking at here. Okay, so that's what you're trying to do here, trying to check those corner points to find out what the maximum profit is. That 3 times some quantity of x plus 4 times some quantity of y equals, in this case, it's dollars that we'll be looking at here. Okay, so we're going to check all those corner points. So the first one here, I'm just stepping through it so you understand what we're doing here. 0, 0, of course, you can see that's just 0 profit here. But then we get down to the 0, 6 here. Where is that? That would be up here, way up here, 0, 6. 0x, 6y. Here you put that in. 6 goes into 4 times 6y here, gets 24. 3 times 0x gives you 0. So your profit here is 24 here. And that was that point here. So now the next one is 1, 6. So going up, that's this point here. x1, y equal to 6 here. Put that into your equation. 3 times 1 plus 6 times 4, 24 is going to give you 27. We're going to find out that's our maximum profit here. And then the last other points that we have here was that 3, 4 point here. 3x, 4y that we're looking at here. Put that into your equation. 3 times 3 here is 9 plus 4 times 4 of y here is what, 16. That gives you 4 times 4 is 16 plus 9 is 25 here. And then that last point was 3 here. 3x, 0y at this point here. Put that into the equation. You're going to get 3 times 3 here is 9, and 0 times 4 here, or y, is 0. So you get 9 here. Okay, so what we've done here, we graphed it out, and then we checked our corner points here. The other thing is you have to be concerned about your maximum profit is either at your corner points or along some edge in that feasible region here. Okay, so this is just doing it by hand here. All right, so we determine our profit here based on our profit equation, based on our feasible region, based on our intersection of the lines here. We come up with our maximum profit at x equals to 1, y equals to 6 here. That's our maximum profit point here. Okay, so maybe let's go over here and let's look at what we're talking about here. Now, this sort of looks at it in, adds what we're doing here in this graph here. It's the same. Those constraints create a region or plane here that we're looking at here. But now we're going to lay it out in terms of those numbers of those profits that we came up with here. So the key that we're going to be looking at here is what they call that gradient vector line here. That's that, in this case, it's that red line. We started out at 0, 0 point here. And the gradient vector line falls on that point here, that 3x, 4y. And those are really the coefficients of that profit function here. And this gradient vector line, we're going to find out that is the steepest portion of the graph here when we look at it in 3D here. But that's the idea that you're talking about here. So it's all the gradient line here. It's always based on the coefficient of that profit function that we're looking at. That, remember, it was 3x, so 3 represents our x here in that 3 point here. And 4 was the coefficient for our y. 3 was the coefficient for x. 4 is the coefficient of y. So that becomes, y becomes our point here at a 4 here. So looking at our graph here, 3x, and it will be 4y here. And this is a key point here because this is how this works here. So you determine your gradient vector line. Now, you have profit lines, or what they call level curves, or what they call equal profit. And those are based on a 90-degree. This gradient line, these level lines, and you can see I'm coming across here, I got all these different level lines here. Actually, the computer did this, printed them out here. But if you knew nothing else here, nothing else, and you knew your gradient, you lay out your gradient vector line based on your profit function here, you know that these level lines are 90 degrees or perpendicular to this gradient vector line, or this profit line here, or in this our gradient line here. And along these 90-degree perpendicularities, all these different levels here, that profit at any point in here, that profit is the same here along those lines. So if you're up here at such and such a point, x equals such an amount and y equals such amount. If you go down over on this side, same thing here. You got a greater increase here in x, but a lesser increase in y. But nonetheless, you're going to come up with the same profit along on these different lines here. So that's the key point here. And then one other thing here to look at, if we looked at, it looks like we've got sort of a gradient line in here. But, okay, so let's go back and let's look at these two different key points here. So that profit here at 3, 4, that 3x, 4y, put that in your equation here. We came up with 25 here was the profit at that point. And then this other point, this was our maximum profit here. 3 times x was 1 here, plus 4 times y here of 6. That gave us 27. That was our maximum profit here. And it sort of looks like, not to be fooled here, but these we can look at it magnified here. But these level curves or these equal profit lines here, you can see there's going to be a difference here because your gradient here, your profit here is 25 is less than 27. They don't. The line connecting them doesn't fall on that level curve here. So let's just look at that here. That's the only point I want to make here. So the point is with our gradient vector line, we can establish that, and then just looking at anything perpendicular to it gives us how much of x and y we can be looking at here. So if we, just to make a point here, the intersection was not on the gradient line. So if we look at it here, and I got it kind of magnified here just to look at it. We had it over here, so I'm just showing a magnification here, only to make that point here. But the idea is, based on this, if you just take your gradient vector here, figure out what that is, start out your 0, 0, and this is a 2D plot, 0, 0, go up to your coefficients here and your profit equation, the linear profit equation here, and then you can determine what different mix you have between your x and y quantities here to come up with whatever profit you're looking at here. So if you're looking at a line here, that's the only point I'm trying to make here. Okay, so that's how you would determine your different, looking at profits and different mixes between your y and x here, products that you're making. Okay, so that's from that's from our perspective here. But let's go down and let's look at 3D down here. Okay, so what I've done here in 3D, I just graphed everything out. You can see the green area down in here, and I got those lines here. Those where our line intersects here at, that we have here. The red one was that x equals 3, and then we got the green one here, y equals 6 here, and then we got that other blue line that we're talking about. So I'm just looking, here is our y-axis here, our x-axis here, and they have all different scalar amounts here. I'm showing it in a square or cube deal here, but you have to really look at the scalar amounts on each side here. And then the z-axis here, that acts as our profit line here. Okay, so looking at it in 3D, what I've got this checker, or this pattern here, this plane that we're looking at. This is a 3D plane here, and it's really a projection off of our feasible region line here that we're looking at here. Okay, so the idea is here, just looking at this gradient line, I'm showing that in red coming up from 0, 0, and I'm showing 25. That was that profit here when we are sitting at 3x, 4y here, projecting it up here, and that's where we got the profit here. Those were those level lines that we're talking about. This is our gradient vector, and those level lines would be perpendicular to it here. But looking at it from a 3D, because that's really what you're looking at here when you're looking at it in terms of you actually have 3 different dimensions, x, y, and then z was your profit in this case. So we have here for that first, with the red line going up here, and then we have the red gradient line here. And the point is here, this gradient line, that's really where you're going to have the steepest slope here. That's the steepest slope on this plane here. So nonetheless, just to view it that. Okay, so we're coming up from 0, 0, and then we're projecting up here in both cases at 3x, 4y here. And then we've got, this is, okay, so that was our profit here at 25. And then our max profit here at 3x and 4y was at our point here, 1x, 6y here. just plugging that into the equation. Remember, we come up with 27 here as a maximum profit. And I'm just showing the projection here. This is with that blue line, and it's projecting right through that plane here. Just to understand it, it's kind of nice to look at it in 3D here because it gives you a feel for what you're looking at rather than just looking at plain old numbers here. We had a pretty good idea by looking at those level curves and those gradient vectors here, adding those to our 2D plot here. But when we added it, looking at a 3D plot, it gives you a pretty good idea what's going on here. Okay, so the feasible region of the profit here is really that checkered or that 3D plane here that started at 0, 0, and then it moved up here, and the steepness was in this direction here. Okay, so I guess we've looked at it in terms of x, y, and z-axis here, and the z-axis acted as our profit here. Okay, so that's what we're talking about here in 3D. And then one last thing here, if we go over and look at it over here, just to make a point here, those level curves equal profit. A little hard to see, but those are what we were talking about up on our 2D graph here, those level curves. This blue line here is our gradient vector here. That vector starting at 0, 0 and going up to 3, 4. It's actually projected up here along on our profit, our plane here, our 3D plane for our profit. But those are the lines here just to make a point, just to see that looking at it in 3D here. Okay, so that's it. And then one last thing here. Okay, you go through all this. We went through all this whole deal, stepping it through it number by number here, and looking at the different plots and coming up how we'd handle a problem like this here. But computer application here, I'm just using MapleSoft, an optimization function. All you do is you just put in some function here, LPs solve here, and then you just put in the in this case we're going to try to maximize that was 3x here plus 4y, and then it was subject to those constraints, x equals 0, y equals 0, and then we had x less than or equal to 3, y equals less than or equal to 6, and then our x plus our y here had to be less than 7, and then we said hit maximize, enter that into your, in this case, the computer function or the software function that we have here, and it gives you the value here. Maximum profit of 27 here. That's what we determined. That was our maximum profit. And the coordinates, x equals 1, y equals 6. Just that simple. So I've cross-checked what I've done here by going through and setting up our different tables, our linear equations, and then graphing those equations on an XY plot and everything. And we just cross-checked everything here and came up with the right answer here. So there's many different software packages that we'll be looking at, or calculators. And of course, we went through just a very basic example here just to get an understanding of what it is. But you can understand if you're going to have some real complicated linear equations, in any number of them, you could have many different equations involved in this. There can be, hundreds of different equations here, but this gives you the basic idea what you're doing here. But using some software package here like MapleSoft really is handy, and it comes quite handy. And you're also going to get the different plots that we looked at, those level and those gradient vector plots and so forth. It comes off just using one of those software packages here. Okay, so that'll end our discussion here on in this case we looked at maximizing some linear functions here to maximize some profit here. Okay, so that'll summarize our discussion.